This meeting is being recorded. So I've started the recording. You're going to allow me now to mute all of you such that you don't have any noise in the background. And those who may have some questions, we shall use the chat to send in those given questions that you may be having. But allow me now to first ask whether Shalom you are on. Shalom, you could raise up your hand. Arthur. Okay, good. Arthur is here. Arthur, Emilia Joy, are you on? Joy, Arthur. I'm checking out my presenters. Emilia Joy. Joy is not yet here. Joy, in case you are on, you let me know. Then Mushunguzi Joshua. Joshua Mushunguzi, you could have your hand raised also. Okay, Mushunguzi is here. Okay. Good. Okay. So, Joy. Okay. Thank you, Joshua. Let me now see whether Joy has come on because you'll not be able to unmute. Okay. Emilia Joy is here. Very good. Okay. Okay. I want to welcome everyone now. Thank you so much for turning up for this session. Today in this session, we are going to be discussing physics, and let me hope everyone was able to receive the seminar questions. The seminar questions were sent in your groups. Those seminar questions were sent in your groups. Okay. Okay, those seminar questions were sent in your groups, and everyone was asked to try out as many numbers as you could. So I think I've not gotten the right piece, but those are some of the seminar questions that were sent in your groups, and those are the seminar questions that we are going to be discussing during this time. So I want you to pay attention. In this seminar, we are going to have another activity, and that activity is going to be, we shall have a quiz in the course. As we are going in for a break, we shall have a break of 20 minutes, and that will be a quiz. We shall be online, and then we shall find out who the winner is at the end of the day. So we are going to be able to discuss 4 numbers to 5, depending on the time that we shall have. And I want you to pay attention, and then we shall proceed. Debbie, we cannot, you don't have your microphone on, so we shall not be able to get you. So Debbie, enter with your audio on, so as to be able to hear us. Allow me now to invite our first presenter. Our first presenter is going to be Arthur Sharon, and is going to be taking us through mechanics. Then we shall have Mushunguzi still coming, and then okay, we shall first have Arthur coming with the mechanics. We shall have Emilia Joy coming with electricity. Then we shall have Joshua come back with the mechanics. Okay, thank you so much. Arthur, you are welcome.
Okay, thank you. Okay, good afternoon, everyone. Thank you very much, Mr. Kaziva, for the opportunity. I'm going to go through number 3 and number 4 of this seminar. And number 3 was talking about pressure. It's about pressure. And number 4 is about work energy and power. So now number 3 was about, part A was saying that define pressure and its SI units. So pressure is the force acting normally per surface area, and its SI unit is Newton per meter squared or pascals. But we this is the symbol for the symbol for Newton per meter squared, and pascals. And as we can, as 1 Newton is equal, 1 Newton per meter squared is equals to 1 Pascal. So if I get like 1,000 Newtons, 1,000 Newton meters squared, it is the same as 1,000 Pascals. So explain why one feels more pain when pricked with a needle than when pricked with a nail. State the assumption made. So in a needle has a smaller surface area than a nail. So the needle it will bring a more pressure since it has a smaller surface area, and the pressure is into a smaller place than for a nail. So the way we state it is, in a nail, the driving force is applied on a smaller surface area than a nail. In a needle, the driving force is applied on a smaller surface area than a nail. Hence, the pressure is higher in a needle. So part C of number 3 is, with the aid of a diagram, describe how you would show that the pressure of a liquid is independent of cross-sectional area and shape of a container. So here is the diagram, and there we see many tubes, like many tubes with water inside them, and they're all on the same level. So the liquid is poured into the tubes, and all of them be on the same level, meaning that the liquid pressure is the same, and on any level that's the same. Like the liquid pressure is the same on the same level. Like for example, if you look at level A, B, C, D, E, the liquid pressure is the same at that point, yet they have containers of different shapes. So the liquid pressure is, so this shows that liquid pressure is the same and independent of the cross-sectional area and the shape of the container. And now when we go to question 4 says, part A says, define the following. So we are going to start with a joule as a unit of work. A joule is the work done when a force of 1 Newton moves an object through a distance of 1 meter in the direction of the force. So yeah, I think that is very clear that a force of 1 Newton moving an object through a distance of 1 meter in the direction of the force. That's to be a direction, because this is work done. And yeah. So next is a Newton, and a Newton is a force which gives a mass of 1 kilogram, an acceleration of 1 meter per second squared. And the third one is a watt. A watt is a unit for power, and a watt is the power developed when work of 1 joule is done in 1 second, because power is the rate of doing work, and work is SI unit is joules, and times SI unit is seconds. So a watt, 1 watt, is a power developed when 1 joule is done. When work of 1 joule is done in 1 second. So part B of number 4 is, a boy of mass 50 kilograms runs up a flight of stairs of 20 steps in 10 seconds. If each step is 25 centimeters high, determine the power developed by the boy. So the unit of power, the way we find power is work done out of time taken, because power is the rate of doing work. So it is like work per time, like joules per second. And joules per second is the same as watt, a watt. So the formula, so we continue as saying work done is the force is a product of force and distance in a directional force. So we say work done out of force times this, work done out of time, which is force times distance out of time. Well, our force is 500 newtons, since the boy is 500 kilograms, and the acceleration due to gravity is 10 meters per second squared. And then the distance he has moved is 500 centimeters, but it's not the SI unit for length, so we change it to meters, where we shall get, but the way we get 500 centimeters is there are 20 steps, and each step is 25 centimeters. So you multiply and get 500 centimeters, where we shall get 5 meters as a, when we change it to the SI unit for length, which is meters. Then time is 10 seconds. Oh my God, sorry. So power is force times distance out of time, where we have our force as 500 newtons times the distance, which is 5 meters, out of the time, which is 10 seconds. We shall multiply 500 times 5 and get 500, and out of 10, that shall remain with 250 watts. But 2,500 out of 10 is the same as 250 joules per second, which is the same as 250 watts. So part C of this number is saying define efficiency as applied to simple machines. So efficiency is a ratio of work output, work input expressed in a percentage. And that's the formula for efficiency. I've put it there so that we can have it, but it's not used. Okay, like you don't put it in the question. And also, we also know that efficiency is mechanical advantage out of velocity ratio times 100%. We never use it into a definition of like saying the ratio of mechanical advantage to velocity ratio expressed in a percentage. We always use this is a standard and only definition of efficiency. You can also express it like when you explain what work output is. I can say, okay, you can, I don't know how to express it, but like you can say the ratio of, this is the ratio of the work done, work developed or done by a machine to the ratio of the work put into the machine, like making the work output and work input, like making the statement lengthy. But this is a better way of explaining it, and it is precise. So then part 2 of C says, describe an experiment to investigate the relation between efficiency and load using a block and tackle pulley system. So we shall use a block and tackle. So the procedure is we are going to use a block and tackle pulley system that has only 2 pulleys, and this is the one, and we shall put loads onto the effort pan and also the load pan, like of known masses. And then after that, the load is going to, we first put on the load. So when we put a mass on the load, the thing is like, it has to have an effort to carry the load. So we have to put something onto the F40 pan. So when we are putting something on the F40 pan, there's a certain velocity, steady velocity that the load will rise at a certain velocity that is steady. So you do it with all other masses and then record in a table. And the velocity ratio and efficiency are calculated from their formulas and are entered in a table. So like you enter the load here and the effort you put, and then you find the mechanical advantage and the efficiency using this formula and this formula. And then if you want to find velocity ratio, but you have to find velocity ratios to find efficiency. So velocity ratio of this machine is found by measuring a pair of corresponding distances moved by effort and load. Because remember that velocity ratio is effort distance out of load distance. So we have to get like corresponding distances, a pair of corresponding distances, you get a ratio, and you use as a velocity ratio. So we note that there is less load. So in this experiment, we note that there is less load is the weight of the pulley of the wheel, the lower block of the pulley that is swinging, because it has to be carried as well with an effort. Then and also the string, the weight of the string, and also the friction in the string and also in the bearings of the pulley, the friction. So the friction varies with the load, but it's small in most cases. And although useless load varies, it becomes a smaller proportion of the total load as the total load increases. Hence, the mechanical advantage increases with load, and efficiency also increases with load. This means that as the load will increase, but there will be a very small proportion, like the proportion of the useless load it is a very small proportion, even though the load increases, it will always be that very smaller proportion. It will become a smaller proportion. So that means that the mechanical advantage will increase because the mechanical advantage and the load are directly proportional, as well as efficiency and the loads. Like if the mechanical advantage increases, if the load increases, the mechanical advantage will also increase. And if the load increases mechanical advantage, it's also increasing efficiency. So yeah, and then this is the graph as to what I was explaining, that the load is increasing at the same time efficiency is increasing. So this is a graph showing the variation of efficiency of the pulley against load. And due to energy wasted in overcoming friction, the efficiency never reaches, it's always less than 100% because of the friction, energy wasted in friction and also in raising moving parts. Like for example, if I'm to take back to this, no, let me just, if I'm to take back to this pulley here, you see this swinging part here, like effort is wasted to carry this lower block of the pulley. So let me continue to what I was saying. So yeah, this is how the experiment is. So that, yeah, I hope I brought it out well. I'll see the questions. So now next, the last part of the question of number 4 was talking about why is the efficiency of a machine always less than 100%? So it's always less than 100% because some energy is wasted in overcoming friction, and also some energy is wasted in lifting useless loads, like the weight of the rope, the weight of the lower block of the pulley. So, and also the friction between the rope and the wheel, and also the bearings in the pulley. So yeah, that's what I have. Thank you. Let me wait for, are there any questions?
Those having questions, raise up your hand and then you can ask. Okay, Treasure, unmute.
I did not quite understand the variation bit of it. What varies with what, and what loses out, or what is smaller than the other.
I beg your pardon, I haven't heard well. I beg your pardon.
Okay, Sharon, you are going to repeat for her how efficiency varies with the load. She has not understood well Okay, UMMY, unmute. UMMY.
Well, me, I didn't understand the experiment.
Okay, so the experiments. Okay, then Janet. Janet,
Yeah,
unmute.
part serum and two. The experiment, the explanation on experiment to investigate the relationship.
Okay, experiment. Okay, then
Yeah,
lastly, Ben. Ben, unmute.
It's like on 3B, he didn't give us the assumptions.
3B,
Question
he didn't
3B.
give you the question 3B. Okay. Why one feels pain? Okay. Then lastly, Mulindwa. Mulindwa, you're the last person. Mulindwa, you are the last person. Mulindwa, unmute.
Hello, Master.
Yes, continue.
Hello.
Yes, go
Master,
on, go on.
I've just arrived here and I'm sorry. I just need you to send the question again. And I'm seeing the experiment and actually I'm not getting you well.
Okay, the questions are on the WhatsApp group, but we are going to try. In case anyone has them, please drop them here in the chat. Those who still have some questions, can you place them in the chat? Okay. Okay, Arthur, you can first explain again the experiment.
Okay. In this experiment, I'm going to use an example of a pulley which has a block and tackle. They say using a block and tackle pulley. So I'm going to use a block and tackle pulley which has these two pulleys here, and one is in air. So now we said we investigate the relationship between efficiency and load using a block and tackle system. So now, without thinking about the experiment, load and efficiency, if it's followed to, if it's okay, if load increases, efficiency will increase, and also mechanical advantage will also increase because they're all directly proportional. And now when we come back to the experiment, we are going to like this is like a practical table, like for practicals, where you like repeat over and over, like you get a certain mass put here and a certain mass. Okay, you get a mass and you put here and you see how it has raised and you calculate and things and so on. So now in this experiment, we have two pulleys. I mean, sorry, two pulleys and an issue like a known mass of is put onto this, the load pan, and then you put different kinds of masses onto the effort until the load moves at a steady velocity. So you keep on changing for the load and the effort, and then you find out okay, you calculate the things into the table. You calculate the loads, effort, mechanical advantage, and efficiency into the table with the formulas that are needed. But like load and effort, they are straightforward. So mass is, then mechanical advantage is load out of effort as its formula, and efficiency is also shown there. But now when you're calculating efficiency, we shall need to find out velocity ratio of the machine. And velocity ratio of the machine can get to know by you can get to know by
Jackson, Tata Jamila akuyita. Tata Jamila, kwako.
Velocity ratio of this machine may be found using the distances moved by the effort and distance, because we all know velocity ratio is effort distance moved by the effort out of distance moved out by the load, because it's a ratio of effort distance to load distance. So now that we have got to know the velocity ratio, we have mechanical advantage. We can calculate the efficiency. And then when you increase the load, as long as you're increasing the load, like as you keep on increasing the load, the efficiency of the machine will increase. So now that's what the graph was showing. So now when we go to this part here, we have noted that the machine has a useless load, has something that is slow, that is killing the efficiency not to reach 100%. It's not allowing the efficiency to reach 100%. And that useless load is the weight of the pulley and the weight of the rope. It's a small rope, but it also has weight. Anything that does not float on the earth has weight. And the friction also between the string and the wheel, or the string and the bearings. So there's energy wasted when you're carrying the useless load, but it's always the useless load is always small, as you have seen, because you know the weight of the rope is small. The weight of the pulley might be small in some cases. So, and also the friction, it is a minor thing. But so now what I'm saying that when you increase the load, the portion for the useless load, this weight of the pulley and so on, it has a smaller portion into the whole load of the pulley, the load of the real load, like for example, the load that has been put onto on the load pan. And now that's the total load, but now there's a useless load, which is the weight of the pulley and so on, which is a smaller portion of the total load. So when you increase the load, the total load, the useless load gets a smaller portion. And then, like when you increase the load, mechanical advantage increases. So mechanical advantage is increasing, and when you increase mechanical advantage, you're also increasing efficiency of the machine. So now in this graph here, so now the load is increasing and the efficiency is increasing, but this is never in friction caused between the rope and the bearings, and also because of raising moving parts of the pulley, like the lower block of the pulley, it moves that lower wheel. So I think I've brought it out, but let me see what your question, if the question is answered. I don't know, Mr. Kaziva, I can also help on this part.
Okay, thank you so much, Arthur, for the presentation. I'm going to sum it up. May I ask you to allow me to share my screen? Okay, thank you so much, Arthur, for the presentation. Okay, allow me now to share my screen. We are going to I'm going to supplement on all the numbers the Arthur has done, and I'm going to start with what is very important. When you look at the first number Arthur discussed, they were asking us for what pressure is and its SI units. Most of the students go off from this point. When it comes to units, we have units, so I'm going to first talk about the units. So we have units that are named after scientists. Take an example, we know a scientist. One of them we can have the science, you have Newton. Newton is a scientist. You have a person, you know, umpires, you know, a science called geo, you know, someone called watts. All these were names for those signs. Volts, these are names for signs. So whenever you are writing units that are named after science name, these are the names, these were their real names. Always the symbol for that unit is always a capital letter. So when I'm writing Newton, I write capital N. When I'm writing ampere, I write capital A. When I'm writing joule, I write J. When I'm writing watts, I write capital W. Volt, I use capital V. So names that are labeled, or names that are after signs, we use capital letters for their symbols. Never write Newton as small n. This one is not a right symbol. However, you should also note that when I'm writing their names, I use a small letter. So you are not seeing, oh, when I'm writing in full, I start with a small letter. Once you write this, this is not correct. When you start with Newton with a capital N, it's not correct. When I start ampere with a capital, this one is also not correct. So always we start with small letters and their symbols are the ones written in capital. When you look at that seminar question, you will notice that for anything that is named after a scientist, be it a definition, it was, when you look at the first one, it had Newton, I had to use a small letter. Be it a joule, I use a small letter. So most of you at times go off when it comes to units. So we need to know how to write units very well. So they asked us to get the unit for pressure. Most of you go on and make a mistake. Units for pressure are Newton per meter squared. But this is what you write. This is no longer accepted. So how are you supposed to write? This is Newton per meter squared. This is the accepted unit. Never write, this is the accepted unit. Never write this anywhere when it comes to physics. Be it the practical bit, be it the other, be it the theoretical bit. Always we use per. We no longer use this slash. So you need to pay attention. However, when it comes to units that are not named after science, for them we use only small letters. Take an example. When I'm writing meters, its unit is small m. Centimeters is small. When I'm writing grams, I write G small. When I'm writing second, I write S. So all these ones are not names for science. So for them, we don't give them respect, but we just write them in small letters. So you need to be able to pay attention. When I'm writing meters, I don't write capital M. When I'm writing centimeter, I don't write capital. These ones are not right. That is one thing I wanted to note that you need to be very careful with. Then the second thing I want to supplement is what you call explaining. They were telling us that explain why someone whose peers using a pin feels much pain than someone maybe using a nail. One, that is an application of pressure. And always when you look at the first question, the first question always has a relation with the second one. So what do you need to know? We know very well that pressure is given by force out of area. And you know, those who have studied proportions, you know very well that this is area and pressure. They are inversely proportional. So pressure and area, they have a relation. So this is, we call it inverse proportion. So pressure is inversely proportional to area. What does it mean? It means that whenever you have an area which is small, the pressure applied is going to be what? Very big. In case the area is very big, the pressure exerted is going to be now small. However, when it comes to force and pressure and force, they are directly proportional. Meaning that when pressure is small, the force is going to be big. Sorry, it's going to be small. When the pressure is big, the force is also going to be big. So in your explanation, let these quantities come out. What causes that? What causes the pressure? The pressure becomes small because of the large surface area. That's why always they ask you, when something has a smaller surface area, when you look at a pin. A pin has a very small surface area. So when the surface area is small here, we have said that the pressure being exerted, the force being exerted is going to be very big. And once the force exerted is big, the pressure is going to be very big. However, when the surface area is big, take an example of a nail. So when the surface area is big, it means that now the pressure is going to be very small. So when the area is very big, the pressure is very small. That's why it is always not advised that when it is rainy season, women are not advised to put on those huge shoes. When it is rainy season, when your car has small tires, you are not advised to move. At least use a tractor, use a fossil that has a very big tire. So that is the same question they are going to ask you when it comes at why is it that an elephant is able to walk on a soft ground whereas the goat cannot? The reason is the same. Why? That an elephant has toes made of flat surface area that exert less pressure on the ground, while a goat has pointed toes that there's a small surface area, meaning that it will be exerting much pressure on the ground. Therefore, it means that now the goat will be able to sing. So all questions that relate around there, you need to explain them in terms of pressure, force, and area. So that is this. They can ask you, why is it someone who is pierced using a nail and another pierced using a needle? Why an elephant is able to walk while a goat cannot? Why a tractor is able to pass through the soft ground whereas these cars, other cars cannot? That is the same reasoning you need to give. Then another thing is what you call unit still. When I'm writing a formula or for any calculation, there are there are four things that we look at in any calculation. What is going to be awarded? One is what you call a correct formula. A correct formula. So when they are marking any number that has a calculation, they are going to first look at the formula. That which formula are using? That power is equal to work done out of the time taken. That is the correct formula. That is the mark for you. Number two, they are going to look at how is your substitution into the formula. So we call it correct substitution. So meaning that the different things you have been given, force, distance, and time, are they correctly substituted? Then we are going to look at how is the arithmetics, how is the mathematics you are working out? Do you know how to divide? Do you know how to multiply? Then at the end, we are going to look at what is the answer correct? If the answer is correct, at the corresponding units, correct answer and units. Are the units correct? That yes. So that is what we are going to do. In case your formula is wrong, that means that you will not be able to get a mark. So meaning you ought to have the correct formula, correct substitution and arithmetics, then go on and write a correct answer and units. And always when you are dealing with power or when you are dealing with any formula, make sure that you are working in correct units. Standard units go with the standard units. When you look at that question, we had the force times displacement out of time taken. When you look at the distance that was given, distance was given in centimeters, but the force you are dealing with was in newtons. The time you are dealing with is in seconds. So newtons and seconds are standard units, meaning you cannot multiply them with centimeters. So always you need to be very careful that now, since these are standard units, also I need to change the centimeters back to standard units, which are meters. So be very careful. It may look very easy, but if at all you don't pay attention to the units, you may end up getting wrong things. Then when it comes to diagrams, or when it comes to experiments, these questions at times are specific. When they ask for an experiment, when you look at that part C, where they say that with the aid of a diagram, describe how you would measure, how would you show that pressure of a liquid, then that question wants you to have the drawing with you, meaning you must have the drawing with you in order for you to do the explanation. So whenever they specify that use a diagram, please go on and use that given diagram. Don't use anything else. Don't just explain. You are going to be losing the marks when it comes to a diagram. So experiments, they must be working experiments. So anything, in case it is a drawing, you have drawn something, let me say the one of transmission. What happens is make sure that anything you have indicated on your diagram also is in your explanation. They must appear in your explanation. Make sure you have a working diagram. Then still now when I come to that same thing of the experiment, when you look at the number that Favor has been explaining, the one of efficiency, they told that describe an experiment to investigate the relation between efficiency and load. Now that experiment does not require you to have a diagram. But why did he include the diagram? He wanted to show you, because this is being a seminar, he wanted to show you how the diagram looks like, that in case the other time they ask for the diagram, then you know how to draw it. But when a question doesn't ask for the diagram, don't commit yourself to draw it because it's not needed. So that question, describe an experiment, does not require a diagram. The diagram and the graph are not needed. They were just to help you understand how that experiment is being carried out. So when you are describing, make sure that you don't need to have the diagram, you don't need to have the graph, but your explanation must be able to bring out what is within the diagram. Take an example. If at all I was describing that experiment, I would say that the pulley system is set up and the known weight is hung at the lower pulley block. A spring balance connected to effort point is pulled at a constant velocity to lift the load, and the effort is read and recorded. Mechanical advantage and efficiency are calculated. The experiment is repeated for different values of the load. A graph of efficiency against load is plotted, showing the relation between efficiency and load. That would be very okay for my describing. So you don't need to write, you need to be precise, but you must have the working points, or you must have the points that make sense. So you need to ensure that you write a correct procedure whenever it comes to experiments. And whenever they don't ask for an experiment, for a drawing, and you commit yourself and draw it, and you mess up with the drawing, then you lose all the marks. Pay attention. When they have not asked you for a drawing, you commit yourself to draw it, then you are going to lose all the marks if at all you make any mistake on that drawing. So never commit yourself if at all they have not asked for it, and if at all they have asked for it, make sure that in your procedures you have a working diagram. Okay, then I'm going to come to still, because we are still talking about machines, allow me to talk about still what we call efficiency. He has emphasized that whenever I'm having efficiency, efficiency is work put into the machine to the work done by the machine. So when you're writing the formula, never define your efficiency as mechanical advantage out of restoration times 100. This is not a definition. This is a formula. So this one is not marked. That is not how they define what you call efficiency. So the definition for efficiency is 1, and it tells us that efficiency is the ratio of the work output to work input expressed as the percentage. Never define your efficiency as mechanical advantage to velocity ratio. Here you have lost all the marks. So pay attention when it comes to the given definitions. Mechanical advantage out of velocity ratio is not a formula. Then this one brings me to what we call velocity ratio. When it comes to velocity ratio, here still we make mistakes. Some of you have your definition. Let me ask people, can you give me what is velocity ratio? By show of hands, you can raise up your hand and you tell us your definition, what a velocity ratio is. Anyone? Yes, Karen, unmute. Karen, unmute.
Velocity ratio is the ratio of the distance moved between the if by the effort the distance moved by the load.
Perfect. Perfect. But now the answer I'm looking for is in the chat. Someone has already mentioned it. Someone has already says that Lorna has told us that is the ratio of the effort distance to load distance. Lorna, that is very wrong. Now that is why I'm heading that when it comes to velocity ratio is the ratio of the distance moved by the effort. If at all you know a seesaw, this is my seesaw. When I have my seesaw, this is my seesaw, and I put something here. This one, I'm going to call it my load. This is what we call a load. And I know very well that this is where my pivot is. So what happens? The distance from load up to here, where my pivot is, that's what we call load distance. When I apply an effort here, when I exert effort here, this seesaw of mine is going to move. It's going to move like this. It will move like this. So the distance from pivot up where I've applied the effort is what you call the effort distance. Now, when you apply the effort, your pulley moves downwards. Sorry, your seesaw moves downwards. So this distance it has moved. When you apply effort here, this distance it has moved is what you call the distance moved by the effort. This distance moved by effort. This load moves up. This is the distance moved by the load. So this movement is what you call a velocity ratio. The ratio of the distance moved by the effort, the distance moved by the load is what you call velocity ratio. For you saying load distance, effort distance, this is not a movement. This is not, there is no anything that is changing. So this one is not correct. So velocity ratio is the distance moved by the effort to the distance moved by the load. However, you are noticing that when the effort moves down, the load is moving upwards. So what are you missing in your definition? Also, don't miss out the word at the same time. That is a crucial word, that all those, the effort and the load move at the same time. So I will say is the ratio of the distance moved by the effort to the distance moved by the load at the same time. So don't miss out the word at the same time because it is crucial when it comes to the definition of velocity ratio. So please, we need to pay attention to some of those key things. Still, I will come and emphasize when it comes to the formulas. When it comes to formulas, please, when they ask you what maybe you have found the density, never write that density is mass out of volume. This is not right. This is wrong. Why? Density is not defined by D. D is not known. This one is yours. You have only created it your own. We don't know it in science. What do we know? We know that the unit for density is rho. So this is the correct formula. Rho is equal to mass out of volume. Once you write D, you are already off the track. You are not writing physics. You're writing something related to the physics. Okay, let me see any other thing. So those are the few things I wanted to emphasize as we go on. Please, and when you're writing the formula, first write it in full words. You don't lose anything. When I'm writing power, write it that power is equal to work done out of time taken. Write it in full words. Don't abbreviate and say P is equal to W out of T. Some of these things are not known. No one, P can stand for anything, can stand for power, can stand for anything. So you need to be very careful when it comes to formulas. Otherwise, I want to end here and we get another discussion. Thank you so much. Okay. Yes, I'm seeing a hand up. Clint, can you ask?
Teacher, I've not understood where you use rho instead of density.
No, density is not represented by D. That is what I'm trying to tell you. That D doesn't stand for density. We don't have it in science. It does not exist that D is density. So never use D. Instead, the right symbol for density is the rho. That's what I'm saying. Okay. Yes, Bena. Bena, you are the last.
So I wanted some work from Arthur.
Okay, the work is going to be shared. The work is going to be shared. Those who have concerns, let's use the chat. Okay, allow me now to invite Emilia Joy to take us through the second number. Emilia Joy, you're welcome.
Thank you, Mr. Kaziba. I'm going to be taking you through number 8. And number 8 came from the topic of electricity. Our question for number 8, part A stated that define the electrical resistance. Electrical resistance is the opposition to the flow of electrons or current through a conductor. Part 2 says, state 3 physical properties that affect the resistance of a metal wire. Here we have temperature, the length of the conductor, and the cross-sectional area of the conductor. The temperature Sanyu, you have something to say? Janet, do you have anything to say? Okay. So we are looking at temperature affecting the electrical resistance of a conductor. In that, temperature increases the resistance of the conductor. The length of the conductor also increases its resistance. The cross-sectional area of the conductor. The bigger the cross-sectional area, the less resistance the wire has. We'll continue to part B, which said, draw the sketch graphs of current against PD for the following. Part I said we draw the one for a metal wire. Part I said we draw the one for a metal wire. So as we draw the graphs, we are having 2 axes. That's the first thing you're going to note. And then on these 2 axes, I'm going to mark current using I, and I'm also going to mark its unit, ampere. Then I'm going to mark voltage with its units, volts. Ami, do you have any question? Ami? Okay, I'll continue since she doesn't have anything to say. When the metal wire, the graph for the metal wire is that one, it's straight. It doesn't curve or do anything. Then the next part we drew was the one of a semiconductor dioide. This one, I still did the same thing, drew the 2 axes, labeled them accordingly, and drew the curve as requested. And do the curve as requested. After labeling my current with I and its units amperes, the PD and its units voltage, and that was a curve for the semiconductor dioide. Then I continued to part C, which said, a battery of EMF 12 volts and negligible internal resistance is connected to resistances 2 ohms, 3 ohms, and 6 ohms as shown below. So as we can see in the figure, there are different resistors that have been connected to the battery. When the question says the battery has a negligible internal resistance, that means that the battery's resistance is 0. Part C continued to say, find the reading of the ammeter A. So from our diagram, we have that we have the three different resistors. But first I'm going to find the resistance I'm sorry about that. I'm so sorry about that. We're going to find the resistance of the two resistors that are in parallel. Here we are having the resistance of two resistors that are always in parallel is always product divided by sum. We have our 3 ohm resistor and the 6 ohm resistor. So we have 3 times 6 divided by 3 plus 6. That is 18 divided by 9, giving us a resistance of 2 ohms. We shall further go ahead to replace the resistors which were in parallel with a resistance of 2 ohms so that we can find the total resistance of the circuit. So total resistance in the circuit is the 2 ohms and the plus 2 ohms, and the second 2 ohms that we are getting at this point are the ones we got after finding the resistance across the 2 parallel resistors. We then went ahead to find the current that is flowing through the circuit, and we used current is equal to velocity divided by PD or voltage divided by resistance. And this gives us 12 divided by 4, giving us 3 amperes. So that's current running through the circuit. So using the formula of, yes, please, Ami. Using the formula of PD is equal to current times resistance, we are going to say that the PD across the parallel resistors is the PD, and we are going to replace our current with 3, since that's the current we got running through the whole circuit, times 2, since that is the total resistance running through the parallel resistors. Therefore, we'll have our PD being equal to 6 volts. The PD across the 3 ohm resistor is equal to the PD across the 6 ohm resistor. Finally, we'll find the reading of the ammeter, and this will be current is equal to potential difference divided by resistance. Here we shall have our potential difference as 6 and the resistance as 3. So we shall have the ammeter reading being 2 amperes. This is because the ammeter was placed after the 3 ohm resistor. Then part 2 of C says the current, we should find the current passing through the 6 ohm resistor. Current passing through the 6 ohm resistor. Here we are having current is equal to PD divided by resistance. Then we shall have 6, since this is our PD across the 2 parallel resistors, divided by the resistance, which is 6 ohms. Then we shall have our current as 1 ampere. So 1 ampere is what goes through the 6 ohm resistor. Finally, we shall do part D, which says explain why a wire heats up when current is passed through it. So when current is flowing through a wire, electrons are also traveling. These electrons travel through the wire. And as they travel through the wire, they collide with the atoms that make up the wire. So when the electrons collide with the atoms, they produce kinetic energy. And in this process, as they collide, kinetic energy being produced, a lot of energy transfer is occurring. And it's this collision of electrons and atoms that causes the heat to be produced. So I finally wrote my explanation as the electrons travel through the wire, they collide with atoms that make up the wire. During these collisions, the electrons transfer some of their kinetic energy into the atoms of the wire. Therefore, as more electrons collide with the atoms, the wire gains more kinetic energy, and therefore its temperature rises. That was question number 8. And I think I can receive your questions now.
Those have questions, raise up your hand and ask.
Like
Yes,
I wanted to ask you, after the lesson, are you going to send these answers to the group or what? Because you're first. Yes?
Mr. Kaziba said the answers will be passed on.
Okay.
Lena?
Yeah, and then for the part of the reading of the ammeter, I didn't get you well.
As I was handling the reading of the ammeter, I went through a number of different steps. First thing I did was to find the resistance in parallel, the resistance of the two resistors which are in parallel. And I found these two using the formula that is used to find the resistance of two resistors in parallel, which is product divided by sum. This applies for only two resistors in parallel. And here we had 3 times 6 divided by 3 plus 6. We therefore had 18 divided by 9, which gave us 2 ohms. I then went ahead and told you that these resistors, which were in parallel, since they gave us a 2 ohm resistance, it is what I have used here to indicate that. So instead of having the 2 resistors which are in parallel, I'm indicating it as one resistor, a 2 ohm resistor, since their resistance is 2 ohms. So with that, we then had the total resistance in the whole circuit being 2 ohms, these 2 ohms that are up here, plus the 2 ohms which we got from the resistance in parallel, and that gave us 4 ohms. So in the whole circuit, there is a total resistance of 4 ohms. I then say that we are going to find the current that is running through the whole circuit. And we are going to do this by saying current is equal to potential difference divided by resistance. Our potential difference is 12, and we are dividing it by the resistance of 4, because 4 is the total resistance in the whole circuit. So we therefore have a current of 3 amperes running through the whole circuit. So using a formula of potential difference is equal to current times resistance, and keeping in mind that the PD across parallel resistors is potential difference will be equal to the current in the whole circuit, that is 3, times the 2, which is the resistance of the 2 resistors which are in parallel. Their total resistance was 2 ohms. So we are having their potential difference. The potential difference that goes across them will be equal to 6 volts. The potential difference that goes across the 3 ohm resistor is equal to the potential difference that runs across the 6 ohm resistor. So finally, to find the reading of the ammeter, we shall say that current, because an ammeter measures current, so we are saying current is equal to potential difference divided by the resistance. This gives us, we've just said the potential difference running through the 2 parallel resistors is 6. So we are indicating here our 6 divided by the 3, since the ammeter is after the 3 ohm resistor. So that's why we are dividing by 3. So we get our current as 2 amperes. So the ammeter will be reading the current that goes through the 3 ohm resistor, which is 3 amperes. Is that clear? Whoever asked the question, is that clear now? William?
When you are finding the potential difference, is it the same formula you use when you're finding voltage?
Yes, depending on what you have. I think it is the same formula. Raquel?
Yeah, I wanted to ask, how do temperature affects the electrical resistance? I beg your pardon, please, I did not understand that part. Can you please repeat for me?
For that part, I said that when we are looking at the question said, explain how the, you told me to explain to you how temperature affects electrical resistance. When you increase the temperature of a wire, the particles running through the wire as if increase. So they are now running faster, and this is affecting the current that is running through the conductor. Is that what you asked? Raquel, is that what you asked? Okay, since Raquel can get back to us, Janet?
Yeah, in part C, the reading of the ammeter. Now, like in this where they ask us like to find the reading of the ammeter when the resistance is in series. Just want to get some clue of that. Yeah, and the other question is, are we going to get the handouts? Where are they going to drop it? Because getting the handout, because in some steps you are a bit faster, we are not even getting there.
Okay, I'll answer your first question. You said when they tell you to find the reading of the ammeter, when the resistance is in series, yes?
Yeah.
That means, let's diagram here. That means that, for example, where do you think the would place your ammeter? If it's here, Janet?
Yes, I'm getting.
Where exactly do you want your ammeter to be? Because if it is here, you just have, when the resistance is in series, your ammeter reading is going to be the current running through the whole circuit. That is all you need to find. You just, when you reach that part of where you find the current that is running through the whole circuit, that will be your ammeter reading.
It's okay.
ITEL. Whoever is using a gadget labeled ITEL. Pretty. Pretty.
Thank you, Joy. I just wanted to know, what do we do if the resistors in parallel are more than 2?
And then?
What do you do when the resistors are in parallel, but they are more than 2?
When the resistors are in parallel, but they are more than 2, you will use the formula of 1 out of R1 plus 1 out of R2 plus 1 out of R3 and you keep on adding depending on how many resistors you have. So this formula that I've written here applies for 3 resistors in parallel. So if there are more than 3, you add and you keep on adding like that.
I hear they are going to deposit the work, but I'm not in any of the groups. I would like the admin to admin one of the groups so that I can access the work.
Mr. Kaziva, can you help us with that? Lena?
Yeah, and then for the, I had asked you the same question, but then for the part of the 3 ohm resistor and the 6 ohm resistor, from there I still got confused. I didn't get you well.
Pardon?
From the part of the reading of the ammeter, yes, where I had asked you, but then from the part where you talked about the 3 ohm resistor having the same potential difference as the 6 ohm resistor, I still didn't pick.
It is exactly that. When resistors are in parallel, they have the same potential difference running through them. So just like I said, the potential difference running through the 3 ohm resistor is going to be equal to the potential running through the 6 ohm resistor. In this case, if you look at it, you're going to have, we had our potential difference running through each resistor being 6 volts. If you add those 6 volts to the point where they come back to the battery, you're going to find that you add 6 twice, and that is going to give you 12 volts. So you're practically dividing the voltage so that each of them gets an equal potential difference running through it. So if, for example, you had 3 resistors, you would have your potential difference that is running through them being approximately 4 volts. So that's how it keeps on going. Gloria? Gloria, please unmute.
I wanted you to re-echo for me how the length of the conductor and then the cross-sectional area of the conductor affect the resistance of the metal wire.
How the what of the conductor?
How the length of the conductor and then the cross-sectional area of the conductor affects the resistance of the metal wire.
So the longer the wire, longer the wire. The longer the wire, okay, sorry about that, I was getting feedback. The longer the wire, the more resistance the wire is going to have, because now it has to cover a larger distance of particles. For example, if I have to pass through very many people that are together, the shorter distance I have to cover is the shorter distance I have to cover is the less time as if I'll take, the less resistance I'm going to face, the less people I'm going to have to go through meandering, asking, excuse me, this, that, there. But then if it's a long distance, that means I'm going to take a long time and I'm going to keep on telling very many people to excuse me, excusing myself here, there. So the longer the wire, the more the resistance it has. Then when we talk about the cross-sectional area, just imagine you have an area you're going to pass through. If the area, let me say in this area, they put 10 people. If the area is thin, you're going to find it a little hard to pass through these 10 people. But then if the area is wider than the previous area you've passed through, the thin area, and it still has 10 people, you're going to find it easier. So the larger the wire, the less resistance it has.
Thank you so much, Joy. I think here we have very many questions coming in, but allow me to interject just a bit. Like Joy has told you, there are three major factors that affect resistance. That is temperature, length, and cross-section area. When you are talking of cross-section area, you talk of the thinner. So the thinner the wire, the higher the resistance. And when the wire is thicker, that means that the resistance is going to be very low. Why? When there is an increase in the cross-section area, it means that the number of the free electrons that drift along the wire also increases. And this one leads to an increase in the current, which decreases the resistance. So that's why we are saying the longer the wire, or the thinner the wire, the higher the resistance, and the thicker the wire, that is the lower the resistance. When you are talking of in terms of length, what happens that the longer the wire, the higher the resistance, and the shorter the wire, then the lower the resistance. Why? Free electrons collide more frequently with atoms. At each collision, that means that they are going to be losing the kinetic energy to the atoms that are vibrating about a fixed position. What does it do? It leads to a decrease in the velocity of the electrons, which leads to an increase in the resistance. So, but at this level, what you just need to know that when the wire is longer, the resistance is high. When the wire is short, the resistance is very low. When it comes to cross-section area, when the wire is very thin, the resistance is high. When the wire is thicker, it means that the resistance is going to be very low. And these ones can be summarized. I don't know, Joy, you can write R. Write for us capital R equals, write rho equals rho. Rho, okay, rho, then L, so you're writing L, then out of So that is L out of area A. So in order for you to remember all the factors affecting resistance, that is how resistance is related to L. L stands for length. L stands for length. Then A stands for cross-section area. So when you look at it, you are noticing that resistance is proportional to length. That's why you are saying the longer the wire, the higher the resistance. The shorter the conductor, the lower the resistance. And then when you look at the cross-section area, they are inversely proportional. So that's why you are saying when the conductor is thinner, it means that the resistance is high. So you can remember, so note that one somewhere, such that you remember the three factors. So the rho stands for resistivity, but that one you can leave it. Okay. Thank you so much, Joy, for the presentation. Those who still have any other question, please, you can leave them in the chat. I'm going to be responding. Thank you so much, Joy. I want us to have now just a break of 10 minutes. We are going to have a break of 10 minutes before we come in for the next presentation. And what are we going to do? So we have our next presenter is going to be Joshua, but before Joshua comes in, we are going to use 15 minutes to do a quiz. So I'm going to share my screen and we are going to see the quiz is containing things that we have looked on already. So everyone is going to attempt and we shall be able to see now who is leading. So I'm going to share my screen and you are going to follow the instruction. So I want everyone to go to your browser and type joinmyquiz.com. Let everyone type joinmyquiz.com. I can even drop it here in the chat, joinmyquiz.com. Joinmyquiz.com. I'm dropping it in the chat. Tap that link, joinmyquiz.com. So those who have reached there, they are going to ask you for enter join code. Enter the join code. So put in this code. So I want to save one there. We are using 15 minutes only, and we have to come back here at exactly 3:45. So put in this code.
Where you have not seen anything. Like where are your messages?
Join my
okay. So Joy, in case Arthur, in case you are seeing anyone getting stuck, so join myquiz.com, put in your browser, those having Google, those having Chrome, or tap on that link I've given you. Then after putting this code and put in your name, I want to first see people joining here.
Which link?
Put the code, put the join code. I want to see
which link?
I'm going to tapping.
Yeah, joining before we start. It means we shall be leaving some of you behind. So put in the code. The code, we are going to do a quiz checking our understanding. So put in the code I've said, click on that link that is in the chat.
Enter the code.
Click in that link that is in the chat. Okay, good. Then the code we are using is 304. When they ask for the code, enter join code, put 304866. Put that code. I want to see people joining. I want to see all of us 100 joining.
Join the games.
Put the code. Put the code. I'm not seeing you. People, let's
sign up.
Are you joining the quiz?
Are we there?
No.
Anyone who has reached there? Anyone who has reached there?
Yes, sir.
Join my quiz. Put that code. Are we good to start? I'm not seeing people joining. I want to see people join.
Join.
When they tell you join code, put 30486.
Does it mean that we should first go to the wall?
Sir.
Six. Arthur and Joy, have you?
Sir.
Joy, have you been able to join?
First, we are stuck.
Enter joining code.
We are stuck.
Yes?
We are stuck.
What is it saying?
I'm not seeing any message which you are saying that we click there.
Okay. I want okay. Okay.
You are playing.
Arthur, have you seen the code?
Yeah, I've seen it.
Sir, me have not seen.
Okay, can we start?
No, me have not seen.
Click on that link.
Okay, have you been people joining? Finished?
No.
Has everyone finished?
No.
No problem.
Finished?
No.
I want to see the prayers entering. Where are you getting challenges?
I think we know the page because they have entered.
Yes? What are you saying?
I think you should reload because I see we have entered. Here it says waiting for the host to start.
Waiting for the host to start?
Yeah.
We have not entered.
I think you reload.
You have not yet entered.
I have not entered.
Arthur, enter.
I have
Say
entered.
join.
Have
After
not
putting the
entered.
code, say join. After putting the code, say join. Press join. Yes?
For us, we are stuck.
Let me reload in case this one is failing. I'll give me a minute and reload again. Okay, the code is there. Good. Very good. I'm seeing people there. Now we are ready to get okay. So we have started. You look at the screen here.
Join a game, join the what?
Look at that. So start. So you look at the screen. Yes. So find out your position. You look at the screen, find out your position.
Excuse me, sir. Where should I join?
Starting. Question is it? Question. Mango seedling brainstorming kutiwa ni okupima diameter. Ono game. Ile mpenzi. Dutole kwa ile moya kwa yingo. Little games. Any questions? Can we take the together?
We attempt advanced physics.
What measure the base of
the pressure at the base of the
your question. The question here, what them
what is the pressure at the
What 16 minutes.
C'est la pointe où les questions là. Alors, na dudu kito. That the glass 25 when immersed in water, the block appears to be
Are we stuck? Okay.
The attempt a quiz. Savoir quand contains par density, this is to a depth of the pressure at the base of the reservoir. Force times this says over what a mode by no, don't two forces This acts the right arm of the second force is
So we have 4 minutes. We have 4 minutes.
hippopotamus can easily walk on the mud. Excessive pressure on the ground and it goes. How many significant figures are there in
Efficiency of a machine is the ratio of work output to work input.
Okay, let me allow you to. Okay. Okay. You are. Let me see. Okay. Hope we are progressing. We have a few minutes to go. So I'm going to cross. Let us see who's winning. So who's winning? So it is Asasla Lena winning. So it is Asasla. Okay. So I'm crossing. I'm ending the quiz now. Okay. Okay. So our winner is Yeshua Mulinzi, followed by Siin, followed by Faith, followed by Gideon, Arthur, so that's how we have performed. Okay. Case is there. So I'm scrolling. So just look at the screen and what is your position. Okay. So that's how you have. So we have only captured the first 48. Okay, good. Okay, let's now the sharing, and then Joshua. Joshua. Joshua.
Yes.
Okay, Joshua, you can now take us through the presentation.
I think I'm going to start with my question. We are going to discuss. We are going to discuss.
Now.
Joshua,
Number
one that is poor. Joshua, can you tell people? Let me first mute all everyone. Joshua, unmute now. Joshua, unmute. Joshua, unmute. Joshua, your network, can you unmute? Joshua, can you unmute? Joshua, unmute. Since I'm failing on Joshua. Joshua, unmute. Oh, okay, sorry. Joshua has dropped off. Yes, Viola. Viola, unmute. Viola, unmute. Yeah, I'm seeing your hand up. Okay, okay. I think Viola. Okay, Emilia, Joy, or Arthur, anyone with those questions? Anyone with those questions with you on the screen there, you could share them.
I do have them, I think.
Okay, go on and share. Go and share those questions. As Joy is sharing the questions. Oh, Joshua is back. Okay. Joshua, share.
Yeah, I think you're now getting me.
Yes, now we're getting you.
Yeah, so we are going to be sharing. We are going to be sharing on number 1, which is basically speaking about motion. But as we start, the first question wants us to what? The first question is asking us to state Newton's laws of motion. Yeah, so now I'm going to share my work in different portions, but let me first start by sharing the definitions of motion or the laws of motion. Now, according to Newton's laws of motion, Newton's first law states that a body continues in its state of rest or in full motion Newton's first law states that a body continues in its state of rest or in full motion in a straight line unless acted upon by an external force. This is also known as the law of inertia. Then the second law states that it states that the rate of change of momentum is directly proportional to the force applied, and this takes place in direction of force. These ones are clear, you just have to know them or you don't know them. But there's no explanation for that, they're just very clear. Then Newton's third law of motion states that for every force, there is an equal but opposite force. Then we are going to go to number 2. Then number two is asking us to, part B is asking us to explain what happens to a person seated in a vehicle when it suddenly is brought to rest. Yeah, now for that, we are going to know, we know that this is all a proof of Newton's first law of motion.
Yes, I was asking that there is an equal and opposite action.
Pardon?
Asking the third Newton's law of motion. If you say reaction, there is an equal and opposite reaction.
Yeah, actually, that could be possible. I think I made an error writing, but it is, for every action there's an equal but opposite reaction. That is, pardon me on that. But yeah, then I think I've answered your question. Then when you go to part B, which is asking us to explain what happens to a person seated in a vehicle when it is suddenly brought to rest. Yeah, now this is a proof of Newton's first law of motion, which states that for every force, there is an equal, which states that a body continues in its state of rest or uniform motion in a straight line unless acted upon by an external force. So since initially when the person is traveling in a car, he's moving in the forward direction. So similarly, as a proof of Newton's first law, when the car stops, the body will continue in that initial direction. Thus, the explanation is the person experiences a forward jerk. That forward jerk is because your body will continue moving even when the car stops. And due to the other external forces that will be acting on you, you'll finally stop. That's why it will be a simple jerk. But if there were no forces acting on you, you would continue moving forward despite the stopping of the car. Hope part B is clear. But that is the answer to part B. Then there's part three. Part three was asking us to draw a graph of velocity against time and use it to find the acceleration of the body. Now I drew a simple graph here. Hope it is kind of clear. Now, in physics, when they ask us to draw a graph, we first of all need to know that in drawing a graph, we have to know the scale of physics. And for many of us that have studied at least practical, at least we know that for a scale of physics, let me try to get my smart board quickly. At least we know for a scale of physics, it has to be in the range of 1, 2, 2.5, and 5. The rest are integral multiples of 10, 20, 25, 50, and we continue going down to 0.1, 0.2, 0.25, 0.05, 0.5. You just continue multiplying by 10 up or dividing by 10 going here. That's where the scale has to be in the range in. Instead, the graph can be meaningful. And thus, we come up with a graph. You come up with a graph as I had showed you earlier, such a graph. You come up with such a graph. Yeah, now, we obviously, for a physics graph, it has to have a title. Then from the title, we also have to, the title as I had showed, it has to have a title. Then it has to have, you have to mark, obviously, you have to label this, the axes, then you draw such a graph, you come up with such a graph. And I think that's clear for the graph. It's not complicated to draw, it's just basics. You just have to know the basics of drawing the graph. Then part I, asking us to calculate the acceleration of the body. Now I want to calculate the acceleration physically. Yeah, now I'm given the graph here. I want to use it to calculate the acceleration. Then, just pardon me a little. Now, first of all, what I know is that I know here that the is 10 meters per second squared. Then I know that the lowest is 0 from where that is the initial for the first time. So now if I'm being asked to calculate the acceleration, I know that from acceleration is equal to v minus u over t. Then I know that the acceleration will be, because now there are 3 phases in this graph. I hope I'm not being too fast. The first phase is acceleration, because you see is literally increasing in speed. Then there's what? Then there's deceleration we have to have. I hope I'm clear now. Someone is saying that I'm breaking. I hope I'm now clear. Then we know for physics, in physics, when you come to calculating acceleration, you're doing motion, there are some basics you have to have. Like, for example, you have to know that acceleration the definition of acceleration. So the acceleration in the first place is the rate of increase of velocity with time. Then
It's me that is not getting well, Joshua.
Then you can ask is of velocity with time, which means we have to see that's the ocean acceleration is equal to v minus. I hope you're now getting me clearly. We know very well that from acceleration is equals to rate of change of velocity over time. We get. Janet, you can ask.
Yeah, I will like you explain again the graph, how you got your acceleration, because there you are a bit breaking. I didn't get it well.
Oh, I was explaining that when we draw the graph, we are going to notice that there is an acceleration in the first part of the graph. And at the next part of the graph, we have a constant velocity, meaning that there is 0 acceleration. And then the last part of the graph, we have a uniform deceleration. Yeah. Now, I was still explaining how to get the acceleration when you're given the graph. When you're getting the acceleration, when you're given the graph, we are going to find out that acceleration will equal to the final velocity minus the initial velocity over time. That's this formula here. Now, here, the final velocity here is maximum velocity, which is 10, which was 10 minus the initial velocity. According to this graph, the initial velocity is here, which is 0. So 10 minus 0 over the time taken to reach here. The time taken to cover this distance.
You're breaking.
Joshua, you are not clear.
Yeah, he's not clear. I think if you just share for us, that work.
Okay. Joshua, could you allow me to?
Is 4. So those are over 4, giving us, I think, an acceleration of 2. Am I now clear? Am I now clear? I'm trying to explain to Janet. I'm trying to explain to Janet. I'm trying to explain to Janet that I did not. Am I now clear?
Yeah, come again, because you're really breaking.
Am I now clear?
Yes.
I'm trying to explain to you that on this from here to here, there's an acceleration because the graph is increasing, the velocity is increasing with time. Then from here to here, there's a constant velocity. meaning there is no acceleration. Then from here to here, we see the graph is decreasing. Thus, there is a what? There is a deceleration. Are you getting me at that point?
Yeah.
Yes. Then I said that now when they ask us to calculate acceleration, we are going to calculate acceleration from final velocity, which is represented by V, minus initial velocity represented by U, against the time taken. Is that clear?
Yes.
Then we know that clearly, according to this graph, the final velocity is this one, which is 10. Are you getting me there?
Yes.
That's why I said acceleration velocity 0 over the time taken to cover this, to reach this velocity, which is 4. Are you getting me there?
Yes.
And thus the acceleration is 2.5 meters per second squared. I think that is clear.
Yeah.
Then we go to part 2, which is asking us for retardation of the body. Now, retardation, we are literally going to calculate it the same way we calculated acceleration. And we clearly know that from acceleration is equals to V minus U over T. We know that the final velocity, now retardation, we are looking at this portion of the graph when we are looking at retardation. Hope you're getting me there. Then when we are looking at that, we know that for this portion of the graph, the final velocity will be this one, and the initial velocity this time around will be here. Now, from acceleration is equals to V minus U over T, we know that since the final velocity is 0, we shall have acceleration is equals to 0 minus initial velocity. Now the initial velocity this time around is not down, it is up, because the person is starting from here, coming down. Thus, this will be his initial velocity, which will be 10. So it is 0 minus 10 over the time taken to cover this. Now the time taken to cover this, we find out it's from 9 here to 12. Thus the time taken is 3 seconds. 0 minus 10 over 3 seconds. Thus the retardation will be negative 3.33. But since...
Joshua?
Yes?
Allow me to interject. I want to say that maybe we are going to end here. We are going to continue with our discussion. We have entered into another class's time. Senior 6 are here already. So we may not be able to complete all the parts. Okay, but we shall start from that point of retardation, and we are going to be sending you all the presentations that we have had today. But before we close, please, we shall have pay attention to the graph. Pay attention, because when they are marking the graph, the key things they look at the title, they look at the demarcation of your axis, then they look at the labeling of the axis. So look at those things when you are looking at the graph. But we shall start from there next time. Those who have not completed the quiz, we are going to do more quizzes, and tomorrow we shall have geography. So tomorrow we have geography, and we shall also have a quiz coming in. So prepare for that quiz. We shall also have to be also a short one, but tomorrow we have a quiz for geography and a geography seminar. The questions are coming in shortly, about 20 minutes from now. You have received those questions. Those who are going to present tomorrow, please let you prepare when you receive the geography questions such that we are ready. I may not take in any question, but just go to the WhatsApp and then I'll be able to reply. Otherwise, thank you so much everyone for attending. Allow me to wish you a good evening. And then I'm going to request the senior 6. You allow me to close this room such that we stop the recording, and then you join again after 1 minute. Allow me to just close the room, senior 6, and then join again such that we separate the recordings. The presenters, thank you so much.